everybody, it's Miss Cantwell, ready for your last lesson video of the year. This week is going to look just a little bit different because we are going to ask that you get your quiz done by Friday morning so that we can put everything in and so that you don't wind up with a missing grade because they're asking us to turn our grades in by Friday afternoon. Okay? It would be a great idea, or it would be helpful to us if you could get this one done by Friday morning. All right, the quiz is still going to come out tomorrow morning just like normal. So you'll still have all day tomorrow and all day Thursday. And I know several of you are working through AP exams and all of that, but just please, take a minute and look at this stuff, okay? Remember, just the same as always, you can always do it as many times as you need to in order to get a grade that you're happy with. And if you need to retake any other quizzes, you can do that as well. So this week in Edgenuity, you're going to be looking at the duality of light, or the dual nature of light. So one of the most important questions in physics is light a wave or a particle? Is it one or the other? And then there's a third secret option, which is, can it be both? Okay, so there have been a lot of experiments done. A lot of scientists did work to kind of figure out the answer to this question. So scientists such as Isaac Newton, we know him. Thanks to him, we have the laws of motion and calculus because he was bored. But he was attempting to prove that light was a particle. And so he showed that, look at this. If I shine a light on a mirror, it will reflect. So it's bouncing off of the surface. And guess what? Particles will do that too. If I take a little ball and bounce it off of a surface, it will reflect. Okay. He also looked at the property of refraction, or the behavior of refraction, and that is just where we slow down or we change speed when we enter a different medium. Okay, so he said, okay, well, if I shine a beam of light into this water, it's going to bend the beam of light because it's going to slow down. Then when it leaves, assuming this is water, that's a weird shape for water, it's going to return back to its original path. And guess what? If I did that with a ball, it would do something like that too. Okay, so he said that it's definitely a particle. This is a particle. Okay. In 1678, another scientist, he theorized that light waves could also reflect and refract. It doesn't have to be a particle in order to bounce off of something or to change speed when it goes into a different medium. Okay, so now we have two things that basically it's true for both ways. Okay, it's true for particles and it's true for waves. Then we have Thomas Young. He did an experiment called a double slit experiment. It's very famous. It's a famous experiment. So here's a single slit pattern here. If you do the double slit pattern here, what you'll see is that light goes through, it bends through the opening. Okay, particles don't really do that. If the particle was going to go through the opening, it would just keep going, maybe bounce back up, but it wouldn't bend like this one is. Okay. Then when we encounter the second screen with two small slits, we see that the bending happens again. And when the bending happens again, the waves start to interfere with each other or cross over each other, and we get this kind of pattern here, where we have destructive interference, the waves cancel out completely, and we have light bands or very bright bands, and that's where they're adding together. So for this one, Thomas Young's double slit experiment demonstrated wave behavior only. Particles don't do this. So the decision then became, okay, well, then it has to be a wave. But we're not done. Okay? So then we had some scientists investigating the photoelectric effect, and that happens when we shine a beam of light onto a surface, and as long as the frequency of that light is above a threshold frequency, we can actually eject electrons from that surface. And it has to be a certain type of surface. It has to be metal. It has to be the light has to be of a significant frequency, but we can see that this happens. Okay, and we can use this, in fact, for solar power options, because if we set up a potential difference, like when we talked about in circuits, so if we set up a circuit where we have high potential over here and low potential over here, the electrons will actually move through that circuit. Okay, so anyway, so what we figured out is that there are things that affect how the rate that electrons are ejected from the surface, and then there's things that affect the energy of these electrons. Okay, so what we figured out here is the kinetic energy of the electrons leaving depends only on the frequency of the light hitting the metal. It definitely does not depend on the intensity, how bright it is. It doesn't depend on the color. It doesn't depend on any of that. It only depends on the frequency. Okay. So then scientists saw this, and we can't go back to, well, it has to be just a wave, because remember, in the Young's double slit experiment, this particles wouldn't do this. They wouldn't interfere with each other. But waves don't cause electrons to be ejected in that way. So there had to be some sort of unifying condition. So our other good friend, Albert Einstein, explained this by describing light as being packets of energy. So it was quantized. So you could release little packets just by causing electrons to move up or down in energy levels. Most people think that Einstein won his Nobel Prize due to his work with relativity, but he actually won his Nobel Prize because of his explanation and description of the photoelectric effect. Okay, so the photoelectric effect helps support the particle theory, and it weakens the wave theory. But we can't really say, is it a particle or a wave? We can't say definitively one way or another. So we can say that it's both. Okay, light travels through space and interacts with itself as a wave, and it interacts with matter as a stream of photons or light particles. So there's even some research in the quantum physics field that talks about it depends on if it's being observed or not, and it depends on, like this says, whether it's interacting with itself as a wave or whether it's behaving as a particle. So it can be both wave and particle, which is unsettling to think about, but that's where we get into this whole branch, like I said, of quantum physics, and you really have to open up your mind for that. Okay, so that's it for this lesson. It wasn't a very long one, mostly because you knew already about diffraction, refraction, and reflection. The only new things were the experiments, and who was in charge of them. Um, I hope you guys are staying safe. Please don't relax your social distancing and your hygiene. Make sure you're washing your hands, drinking plenty of water. I miss you guys. I'll probably send another video next week with like my face so I can tell y'all to have a good summer. But make sure, like I said, you're taking care of yourselves and your families. And also, keep in on your grades. See how they're doing. You still have time to fix anything that needs fixing. Okay, I hope you guys have a fantastic rest of your day, and I will talk to you later. Thank you so much.